Okay.
All right. Good afternoon, everybody. As more people are milling in and grabbing their food and whatnot, so I want to get started and hear more from Dr. Walter Sujansky. Originally from Stanford, did her training many years ago, right from this program. I would love to hear more about that process. Now an adjunct faculty, ongoing interesting industry work that I think we learned a ton from. But go ahead and just tell us, Dr. Sujansky, more about yourself. How you arrived? Why are you working on all this stuff? And you've been very engaged with our community for many months, if not years, at this point.
Yeah.
I've been seeing you secondarily many times.
Well, first of all, thank you for inviting me, Jonathan. It's a real pleasure to be here, always talking in front of colleagues and friends at Stanford. I'll start, as you suggested, maybe just a little bit about me. So this, I realized a moment ago that probably people out there in Zoom land may not get this joke with the photo, but this photo was taken about 20 years ago. So this guy couldn't be here, but he briefed me on this topic, so I should be able to cover the subject matter pretty well.
If it weren't for the glasses, I wouldn't know the difference.
There's a faint resemblance. Well, thank you. That's kind. So quickly about me, as John mentioned, I was a MD PhD. I'm an MD PhD graduate, and what was called the actually it was called the Medical Information Sciences program back when I was in the training program, and then it was section on medical informatics, and then it was BMIR, or now it's still BMIR, and then it's data science. So it's essentially the same program. It's been continuously the same program, just with different names. And so I did an MD PhD. After that, I did not continue medical training. I went out into industry. That was what I decided by the end of my time here, my many years here. That's what I decided I wanted to do with my life. And so I worked for a few startups in the EHR and health IT space. Most of which you've probably never heard of, but some of you may have heard of the last one I worked for called Hippocrates. They do, especially if you're clinicians, they did a lot of stuff with drug prescribing, decision support, and information systems and so forth. And that company actually went public. So I figured that was a good time to leave the startup world. And also I was talking with a lot of people who are interested in seeing if I could help them in various ways. And so I decided it would be more fun to work on a lot of different kinds of projects rather than just work for one company. So in 2003, I started a little consulting firm and kind of built it. The focus of it is what I had been doing and what I've been most interested in, even from the time of my thesis, what I call clinical data engineering, which is really about modeling clinical data, and supporting its interoperability and its use in decision support and research, as well as looking at other aspects of data such as privacy, security, and how it's regulated by the government and so forth. And so the company always remained, this consulting firm has remained pretty small. It's kind of varied in size from yours truly to about 5 people plus some subcontractors, so kind of have been flowed over the years. And we've had a number of different clients, different kinds of clients doing, I'd say that the versatility has been kind of a hallmark of my consulting career, in the sense of wanting to do and doing a lot of different kinds of projects and being interested in a lot of different aspects of the health IT space. So we've worked for pharmacos, health plans, federal, state governments on all kinds of different projects, and one of which I'll talk about today, a little more depth. And then a couple years ago or so, Mark was kind enough to invite me to come back and help start by giving some lectures and then getting more involved and culminating in an appointment as an adjunct faculty member. I call myself an adjunct professor, or is professor like going too far?
You're a professor.
I'm a professor.
You profess.
I profess to be a professor. So, okay, so now I'm an adjunct professor. Back here I'm doing teaching and happy to do advising and help students as well. So, John, I don't know if that covers it.
Well, once you want to dive into the actual other content, but I'm interested more, actually a lot, like, why did you go the industry route versus getting more medical training? Or let's jump to, you started consulting from, how's it work? You just like, I'm a consultant now and I hope somebody calls me. It's not like that, right? How do you get business?
You get a sandwich board.
Right.
Go to AMIA. No, you really have to. So I worked, between that, I worked for 7 years in the industry. So between the people that I knew from grad school, before that I had been at Stanford for 8 years in the informatics program. Since I was doing an MD PhD, there were like several cohorts of informatics people that had gone through and were now working in industry and elsewhere, plus the people I had met. So I had a network by that time. And that's what got me into consulting, is people in my network would contact me.
Asking you for something.
Yeah, they say, hey, can you help? Do you know anyone who can help us with this? Do you know? And I was like, I do, me. I'm working at Hippocrates, so I can't do it.
I got somebody who's well worth the price. Let me tell you that.
So I realized I could make a go of it, or I thought I could, but I did have to, you kind of jump and hope a net appears.
Yeah.
So, and I'd be happy to talk with anyone considering that career path, but I wouldn't say it's the kind of thing, again, you need a network in order to start. You can't come out of school, not have a network and just say, I'm going to be a consultant. Unless you go and work at Deloitte or something where you're a consultant.
I assume it is, mostly, maybe you do, you don't advertise, hi, I'm a consultant, someone please call me. So it's through your network. You just happen to have most of those, your contacts or your work was through somebody you knew through it.
And that's one of the advantages of staying small, because you don't need as much work. If you're a Deloitte or McKinsey or something, or even like a medium-sized firm, now you've got a lot of mouths to feed, and you got to keep the pipeline, and you're running a business, and consulting projects, they start and they stop, and you need new ones. So you always have to have a pipeline, and so you have to go to conferences and have a booth, and so you end up doing, when you're running a firm like that, you end up doing a lot of sales and marketing and less informatics. And I didn't want to do that, so that's why I was kept it small. But
I'm sure a wide range of would be. Do people literally come to you for consultation, like give me advice, or is it, can you like literally write this program or do something, or where?
Both.
Yeah.
Both. I have one client like right now that calls me, maybe once a month, and they have some question about the EHR regulations, the ONC, meaningful use regulations.
Explain that.
Like what? Yeah, help us. We just realized we need to also do this. Help. So then we talk for. I'll do a little research. We talk for a couple hours, and then I'll go from them next month. At the other extreme, I'm doing this project with the FDA where I'm working on every single day. I'm like 3/4 time right now on that project. So that's the range. Obviously, it's better to have. It's good to have a mix, but you definitely need to have sort of an anchor tenant. Instead of like 4 or 5 really tiny projects where you don't know when they're going to call, and so just to make a living.
Is there a little bit more story why bother with this adjunct thing, and you're off doing cool industry stuff? It's sucked back into the educational realm. What for?
Why did I become an adjunct? Well, 2 reasons. One is that the main one is that I like it. I enjoy it. I feel like I've learned something now in whatever few decades of my career. I guess I started working professionally in this even before I graduated. So it's literally been 30 years that I've been working in the field. And so I feel like I could bring some sort of real world experience and knowledge and link it into the academics that are being done here as well. They're being taught, round it out a little bit. And I enjoy doing that. But it's also good. It's good for my career. It's good for me to get, obviously to get consulting. I'm an adjunct professor at Stanford, so that doesn't hurt. And sometimes I do expert witness, like legal work. It's good for that as well. So it's I get that out of it as well.
So there's value to being a professor at Stanford. I'm still trying to figure it out.
Still looking for it. Or you don't know what you got, Mark.
Apparently there's value. People are clamoring to do it. I've never understood it either.
I mean, go ahead and jump into things as you go, but I think that'd be very interesting. all sorts of lessons learned and things you could teach us that you didn't get in training or that we don't tend to train people adequately for an academic environment that they really should know about. I think it'd be cool to hear.
Okay. Well, maybe if there's time at the end, we can talk more about that stuff as well. But hopefully you all will also be interested in some of the details of some of the stuff I've been working on recently. Excuse me. And I need your feedback on it, input and feedback on it in the context of things you're doing to just see if possibly there's any applicability for the data science and data analysis work that you all are doing as well, because that's useful for me in this particular kind of work, especially because it's more general, can apply to others besides my current client. So let me talk about this, since I've billed this talk as about temporal reasoning and inference. So let me jump into that. This is the temporal modeling inferencing research, I guess. I think of this as actual research work. Obviously, not everything I do is researchy. But this is part of a current consulting project we're doing at FDA called the SHIELD project, which is about improving data modeling and standardization for laboratory test result data, including genomic testing data. So there's a lot of facets to this project. But one is that there's actually some more general clinical data modeling issues that are being addressed in the project beyond just with lab data. So basically with all kinds of clinical data, and most generally looking at how to represent the semantics of patients' clinical data in a normalized way, so that's kind of predictable and reliably computable, because that's what's needed to support clinical decision support and data analysis and observational research and using data even for machine learning and so forth. It starts with the data, and no matter how good your algorithms are and your decision support program or whatever, if you can't connect it to the data that you're actually operating on, it's kind of a moot point. So how do you do that? How do you represent that clinical data so you can connect to it and reliably? And one aspect of that, or one specific aspect of that we've been looking at is temporal relationships between events or states that are represented in a clinical database. So for example, the concept of arrhythmia during thoracic surgery. So this is a particular subtype of arrhythmia or temporally qualified arrhythmia, and that's characterized by a relationship really between two events, an arrhythmia and a thoracic surgery, and a particular temporal relationship between them. So how do you formally represent that notion? And how can you reason about it? How can you soundly reason about it or query for that pattern, if you will, in a clinical database and so forth? So that's what we've been looking at. And the start, I was basically tasked with my original task in looking at this was, can we add formal temporal definitions to the SNOMED CT terminology, which some of you may know as an ontology, clinical concepts, to support automated classification and what's called subsumption testing, which I'll talk about in a moment. So the idea is here's two concepts that might be in the SNOMED ontology. Concept A being more general than concept B. Concept A being arrhythmia during thoracic surgery, and concept B being atrial fibrillation during a lung lobectomy. And so, for those of you who are clinical, you'll recognize that the task here is to determine is concept B sort of a subtype of concept A? Is a hierarchy, if you will, or a subsumption hierarchy? Is it necessarily a more specific instance of subtype A? So technically, this term subsumption has a formal meaning. Informally, we call it is a hierarchy, but formally, it's the notion that if something in the world is an instance of concept B, then that necessarily implies it's an instance of concept A. And that's what's meant by subsumption. So if that's true, an instant concept B is an instant concept A, then concept B is subsumed by concept A, and concept A subsumes concept B. And again, for those of you who are clinical, you know that in this case, concept A does subsume concept B because atrial fibrillation is a kind of arrhythmia, and a lung lobectomy is a kind of thoracic surgery. Now in SNOMED, there's SNOMED uses, again, some of you may know, a description logic. Anyone who's been paying attention in Mark's lectures knows that SNOMED uses description logic, which is a system of first order logic that actually allows you to test subsumption relationships through automated deduction. And for those of you under 50, originally this first order logic and automated deduction, this was the original AI way back in the day. This is how people who started AI did AI. They based it all on first order logic and automated deduction and so forth. Things are, it's obviously evolved to something different now, but this is still used in SNOMED CT. And in fact, you can, looking at the structure and the definition of these two concepts, you can infer using automated deduction that if atrial fibrillation is arrhythmia, and if lung lobectomy is a thoracic surgery, and if the relationship during is subsumed by the same relationship during, which it is, then logically that means that the entire concept B is subsumed by the entire concept B. So this is used in the maintenance of SNOMED and for other purposes, and also for pattern matching against data, not necessarily temporal pattern matching, but other types of pattern matching. And so how does this work though? How do we, if we apply that rubric, that logic, how does SNOMED, how does the description logic system know, for example, that a lung lobectomy is a subtype, is subsumed by a thoracic surgery? It can't look at the text of those two strings and know that there's completely different. So somehow you have to represent to the computer that is the case. So how can you represent that to a computer? How can the computer infer that lung lobectomy is subsumed by thoracic surgery? So one way is you can actually tell it. You can program into the system as axioms, basically, that here's a subsumption hierarchy, or is a hierarchy of different kinds of surgeries, and we're just going to tell you that lung lobectomy is a thoracic surgery. Alternatively, there's another way in SNOMED where you can actually define those concepts themselves kind of recursively and say, you can define a thoracic surgery as surgery with an anatomic location of structure of the thorax, a lung lobectomy as surgery with anatomic location of structure, lobe of lung. And if lobe of lung is a structure of the thorax, then again, using this automated logical deduction, you can infer that lung lobectomy is a thoracic surgery. And then using these other inferences, you can then roll that up to finally conclude that the entire concept is subsumed. So this is a system of logic that can work on very large terminologies, and there are various uses of this automated inference for maintaining the terminology and other purposes. But in this case, it's easy to make this inference using the available logical reasoning of description logic. But what if instead of both of the relationships between temporal relationships being during, one of them was during or within 4 hours after? Now, how would we know that the relationship during is subsumed by during or within 4 hours after? Remember what subsumption means again. What this means is that if two events are in a relationship where one occurs during the other, temporally occurs during the other, what this subsumption means that necessarily implies that those two events are in the relationship that one is during or within 4 hours after the other. So it necessarily implies that. And so how would we determine that? How, if we're trying to do trying to determine if these two concepts, if one of these concepts subsumes the other, and that's part of the logical reasoning. Well, one way, well, let's say it's even more complicated actually. And before we get to that, one relationship is 30 to 60 minutes after, and the other is during or within 4 hours after. Now, again, there's the text strings here don't really help us. There's a semantics underlying this. How do we represent that in a way that we can automatically deduce or determine whether this is a relationship exists? And this is useful in the context of SNOMED, for example, classifying all these different variations of arrhythmias and surgeries and temporal relationships among them. So if we want to do that automatically, how do we determine this particular aspect of the problem? It turns out that SNOMED, the description logic system, doesn't have a way of doing this itself. It's not part of description logic, these temporal semantics. But there's no way to use that automated reasoning that I talked about earlier, where you define, the anatomic part is a subpart of that, blah, blah, blah. And you can't do that with these temporal relationships in description logic. So how could you do it? Well, one way is you could manually construct a hierarchy of all these relationships. You can see here the logic of this, that if something occurs after, then it occurs during or after, if it occurs within 2 hours after, it occurs after, and so forth. You could tell the system through axioms that these are all the relationships. So the system doesn't really need to understand anything else except that these particular relationships are in the subsumption. But is there a better way to do this? Is there a way you could develop a model and an inference capability that description logic currently lacks, that would allow the computer to figure out, to reason about these relationships without being told a priori, without every time you add a new one having to put it in this hierarchy in the correct place? Is there a way to represent these relationships in a way that would support automated inference? So the answer is perhaps. So we think so. So we've developed the system that I'm about to tell you about, and submitted a paper about this that we're building as a model for the formal representation of temporal relationships in EHR's terminologies and ontologies, the model component, and an efficient algorithm for logic-based temporal subsumption testing and pattern matching. So that's what I'm going to tell you about now. What is this model? What is this algorithm? And what can it be used for? What are some of the things it can be used for? Then I'm gonna ask you to tell me what else you think it might be useful for, if anything, that you're familiar with. So let's start in defining the model. Let's just start with some assumptions, notation, and so forth. So because you always have to have a foundation for these things. So we'll start with the notion that there's something called the temporal concept, which is a class of events or conditions or states. And an event is an instance of that concept, or an instance of that class. So for example, the headache I had yesterday afternoon from 1 to 4 p.m., that specific headache that I had at that time, that's an instance, that's an event. That's an instance of the temporal concept, migraine headache, which that concept is just an abstraction. And then we define each event exists during a finite interval of time. That we call the event interval, and that each such event interval is defined by a beginning and ending timestamp. IX is defined by beginning and ending time, BX and EX. So you can see here graphically kind of what that might look like, and further that BX and EX are discrete time points on a single fully ordered linear timeline, and all these assumptions, figure in later into semantics and proofs and things. That the beginning and ending point denote a defined minimum granularity of time. That by default we're saying is 1 second, but it could be less. It could be a microsecond if it's important. Make distinctions, temporal distinctions that are more granular than that. We're assuming that the beginning time point is always less than or equal to the ending time point, although they could be equal to each other if there's in the notion of instantaneous events, for example, a lightning strike or the moment someone dies or something like that. That's an instantaneous event. You could have those, or you could have an interval that's greater than 0. And that, just for notation purposes, we also define these functions B and E that apply to the intervals, event intervals. So that B of the event interval X is beginning time point, and E event interval is the ending time point. So that's the basic model that hopefully seems pretty intuitive, or it seems to correspond to our intuitive notion of time. And then we define something, a relative temporal duration, as a duration of time between two beginning and ending timestamps. Two of these timestamps defining the interval for some event, the distance between them, and relative temporal duration could be between timestamps of two different event intervals, two different events. In fact, that's how we're going to use it mostly. And then you can express these at any temporal granularity greater or equal to the minimum granularity, which we're saying is default is a second. So you can represent these durations in seconds, minutes, hours, years, etc. So here's an example, just to make sure we're clear on this notation. What this is saying is the ending time point. Remember, this is a timestamp, the level of a second in time. The ending time point of interval X minus the beginning time point of interval Y, different interval for a different event, is minus 12 hours. Okay, so what does that mean? Basically, that means event X ended exactly 12 hours before event Y began. So here's graphical view of that relationship between event X and event Y at these particular time points. So one thing you can see is that these relative temporal durations can be negative if time point B is greater than, the second time point is greater than the first time point, which it is in this case. And then finally, with respect to these durations, there are fixed conversion factors between all the units of measure, which is important because later we're going to be comparing different relative temporal durations, and it could be expressed in different units of measure, and we always want them to be interconvertible so we can normalize them to the same unit of measure when we do that. And then finally, we're defining something called relative temporal interval predicate. This is where we get to the real meat of things. And what this is that it's a constraint predicate that defines a constraint on the relative temporal duration between a pair of beginning and ending timestamps belonging to two different temporal intervals. And that's a lot of words. But what that means, for example, is in this example, what we're defining the notion that atrial fibrillation and atrial fibrillation beginning at least 1 week and no more than 4 weeks after surgery. That's a constraint. That's a particular statement about an instance of an atrial fibrillation and a surgery that we're saying, that we're specifying as a constraint and denoting as a predicate. So we notationally, syntactically, we use this alternative notation here, BE, and then these brackets 1 hour, 4 hours. And so what that is exactly, the semantics of that is exactly what's in the example above. At the beginning time point of the first interval, IX, minus the ending time point, the second interval, IY, is within this range specified by the parameters there, 1 hour to 4 hours. So this is basically a predicate. This is a parameterized predicate that either is or is not true for any pair of intervals. So logically, predicate, I mean, it's a logical predicate that then can be, that has that status within the first order logic, the model principles of first order logic. We'll see how that works. So here's an example where we can apply this predicate to actual two instances of data, particular interval for a particular atrial fibrillation, a particular surgery. And the meaning here is that we're saying the atrial fibrillation began at least 1 hour, but fewer than 4 hours after the surgery ended. Now that can be true or that can be false for any particular instance of atrial fibrillation in any particular surgery. And so that predicate value is true or false. So the relevant temporal interval predicates are a way of making statements about about that relationship between two events, or the event intervals of two events. Now, there's actually 4 types of such predicates for the 4 combinations of beginning and ending time points between two events. You can see here graphically how those are represented. And again, so sometimes they can be positive or negative. These are just happen to be two different intervals, but you can imagine, one interval being inside the other interval, both of them being disjoint, one being before the other or the other way around, et cetera. And that would entail different parameters, different values for the parameters in the relative temporal interval predicate. So for example, here's a bunch of examples of what these expressions might look like. But here we're saying the beginning of the first event relative to is between 0 days and an infinite number of days after the beginning of the second event. Beginning of the first event is 1 week to 3 weeks after the ending of the second event, and so forth. So these are all expressions, syntactic expressions, and what their semantics are. You'll notice here there's 2 special notations, plus infinity and minus infinity. So these sort of intuitively, these have the notion that there is no limit. And these are important for denoting, really familiar temporal relationships like after. If something occurs after something else, if some event starts after another event ends, you're just saying it's at least its beginning, the relationship between its beginning and the ending of the other event has to be greater than 0, but there is no limit how long after it can be in order to capture that notion. So that's where the infinite. Likewise, if something's before something, there's no limit to how far before it is, in those semantics. So again, the lower bound on that is negative infinity. Okay, so that's the model. It's a lot of information, but let's look at how it might be used. So let's go back to what we were trying to show before. We're trying to make an inference as to whether the temporal relationship in concept B, 30 to 60 minutes after, is subsumed by the temporal relationship in concept A within 4 hours after. And because we already know the relationship with arrhythmia and lung lobectomy and all that, our computation, our deduction of whether concept B is subsumed by concept A depends on making that determination. And so how can we automate that with this model? So basically what we can do is we can represent those 2 temporal relationships using these expressions, these relative temporal interval predicates that I just described. And so the model allows us to represent those temporal predicates. But how do we compute whether one is in fact subsumed by the other? What's the algorithm for doing that? Which is, of course, something that we've also defined. So a way to think about that is logically. This is where we get into kind of first order logic. This is making that determination is basically requires determining whether the following logical assertion is true. If this predicate, we're going here. So it's saying if some pair of intervals satisfies this predicate, it implies that that same pair of intervals satisfies this predicate. Again, that's the definition of subsumption. So that's what we need to determine. Is this logical statement true or not? We want to prove this logical statement, essentially. And so how would we do that? Well, when you think about it, what this is equivalent to, going back to what the semantics of these expressions are, these relative temporal interval predicates, this is saying if the difference between the beginning of interval X and the ending of NDY is at least 30 minutes and no more than 60 minutes, then does that imply that that same duration of time is necessarily greater than an hour, less than or equal to 4 hours? You can see that this actually is pretty easy to compute when you look at it that way, because we're just saying if some value is greater than 30 minutes, is it greater than 0 hours or 0 minutes? Obviously, yes. It's just mathematical truth. If it's less than 60 minutes, or 1 hour, is it less than 4 hours? Again, that's necessarily true. So is at the base level, the inference is based on this subsumption algorithm between relative temporal interval predicates that just takes two such expressions like this, and just spits out whether it's true or false that one subsumes the other. So now that allows us, going back here, that allows us then to make this determination. In this case, it's true. You can see you're looking at those values, but it may not be true depending on what the values are. So let's look at a more complex example here that shows a case where it's not true. So here we've changed the concept. So concept A, the more general one, is arrhythmia occurs during thoracic surgery. And concept B now says atrial fibrillation starts within 30 minutes after a lung lobectomy. So just intuitively, we can tell that concept B is not subsumed by concept A because there's a different periods of time, right? So, but a computer doesn't know that. We know that because we have a whole model of time in our brains and we understand these words, but the computer understands nothing about this. So how does the computer use this model to correctly make that logical inference that we just intuitively make in our minds? Again, so now what this requires, this is more complex because representing that the notion of during, in fact, requires two different relative temporal interval predicates that are conjoined, that are anded. So we need to generalize this concept to something we're calling a relative temporal relationship, which is basically defined as a conjunction of relative temporal interval predicates. So here we just have conjunction of these two. This one's saying the beginning has to be after the beginning of the arrhythmia, has to be after the beginning of the surgery. This one's saying the end of the arrhythmia has to be before the end of the surgery. That's our definition of during, which makes sense. And then again, the atrial fibrillation again is defined as starting within the first half hour after the lung lobectomy. So now, how do we calculate whether this subsumption relationships hold? So essentially, we need to, putting it in the language of first order logic, we need to determine if this statement is true. If these two intervals satisfy this predicate, do they necessarily satisfy the conjunction of these two predicates? And again, reformulating that in using the actual semantics of these expressions, as we did before, we reduce it in a way to this question. But now, notice something important here. When you look at the relationships that we're comparing here, they're all different. They're actually different intervals. This is the interval between the beginning of the first event and the end of the second event. This is the interval beginning of the first event and the beginning of the second event. It's the end of the first event and the end of the second event. So we cannot use that same algorithm to just compare the values and determine whether one implies the other. So what do we do in this case to enable the algorithm to compute this? Well, it turns out that there's a set of logical implications for these relative temporal interval predicates, such that if you know that there's an antecedent, if you know the lower and upper bound within these expressions, it implies a lower and upper bound for the other pairs of timestamps, of temporal intervals. So for example, if we know that the beginning, the difference between the beginning of one event and the end of another is more than 0 hours, less than or equal to 0.5 hours, these implications allow us to then say, we know that the beginning, the difference between the beginning and the beginning is between 0 hours, but there's no upper limit. The difference between the ending and the beginning is also between 0 hours, no upper limit, and so forth. So it allows us to generate implications for all four combinations, if you will, of beginning and ending timestamps. So I won't talk about the intuition of this. You can you can just convince yourself that these implications are based on the fact that the beginning of an event cannot occur before the end, and the end cannot it cannot occur after the end, and the end cannot occur before the beginning. So when you apply that logic, intuitively, you think about it, you can see that there are these implications. You can also prove this mathematically, which we do in the paper, that all of these implications in this table are sound. So what that allows us to do in this case now is, again, this is what we're trying to determine whether this logical assertion is true. We're trying to prove this. See if we can prove this. But we can't apply that algorithm directly because they all had different beginning and ending time points. But if we apply the following rules from the implication table, what essentially happens, we can rewrite that logical assertion at the top as these combinations, because it's actually, because these implications exist, and the antecedent of this expression is actually logically equivalent, the conjunction of original interval predicate and the interval predicates that are implied by that interval predicate. So these are logically equivalent, and that's provable as well. Similarly, for this expression, this conjunction, again, each component here has certain logical implications. So you can prove that it's equivalent to this. And now what we have, basically, we have corresponding interval predicates. So basically, now they're lined up, and you can apply that earlier algorithm to test whether these implications all hold, just like we did before, by looking at just the value, the lower and upper bound values, and applying a simple algorithm. And again, applying logic, what this tells us, provably tells us, is if this predicate implies this predicate, and this predicate implies this predicate, and this predicate implies this predicate, then the conjunction of these three predicates implies the conjunction of these three predicates. That's just a logical theorem, if you will, that you can prove. And so then that allows us, that basically would allow us, if we can show that these things are true, then we can show that the original logical assertion is true. We can prove it. But however, in this case, turns out it's not true. So one of the things we would need to show is that this predicate implies this predicate. Again, that's equivalent to these statements, looking at the semantics. But if you look at, now you've got them lined up, beginning and end to beginning and end. Here we're saying, is it true that if some duration is less than or equal to 0.5 hours, it's less than 0 hours? Again, just logically, no, it's not true. It could be 0.25 hours. It would satisfy the top predicate, but not the bottom. So that implication is not true. Based on that, we cannot say that concept B is subsumed by concept A. We cannot say this temporal relationship is subsumed by this one, and therefore we cannot say this whole concept is subsumed by this whole concept. So that's an example where, a more complex setting, again, we've used the machinery of this temporal inference model and the temporal inference to soundly compute whether this subsumption relationship is true. And you can go on further. I'm going to go through this part quickly, but basically you can also introduce disjunctions of these temporal expressions. So far, we've just talked about conjunctions, but you can extend the model to allow, you can increase the expressivity of the model to allow disjunctions as well. So now we can have this concept down here. If the infection is during the first or the third trimester of pregnancy, is that subsumed by the notion of infection during pregnancy? How do we represent those different temporal relationships, and how do we compute subsumption in this case? So basically, the addition here, and I won't go through all the details, the addition is that we've generalized this expression to allow disjunction, basically to allow any combinations of conjunctions and disjunctions of these relative temporal interval predicates in any combination whatsoever. So anything you can think of that can, any temporal relationship between two events that can be expressed as the conjunction or and with disjunction, combination thereof of relative temporal interval predicates can be expressed by this model. And then further, so now we need to, as far as inference is concerned, we basically, the inference question has come down to proving following logical assertion. Here we have the first predicate. Is it true that if the first predicate is true or the second predicate is true, then that implies that the conjunction of this predicate is true. So again, there's an algorithm for doing that. I won't go into the details of it. You have to convert this to a normal disjunctive form that it's just a disjunction of conjoined temporal predicates and so forth, then showing that one is subsumed by the other. And there's a particular algorithm for doing that. That again we've proven to be correct. Taking stock, basically we have a model to formally represent temporal relationships between pairs of events that allow us to represent any temporal relationship that is expressible by denoting constraints between the beginning and ending time points, respectively, of two intervals, and conjunctions of such expressions, as well as disjunctions of such expression. Any temporal concept we're familiar with or might want to represent that can be represented in that way is admitted in our model. And we've shown that we have a sound way to automatically deduce whether one such relationship is subsumed by another such relationship, no matter how complex they are, how many conjunctions and disjunctions there are. The algorithm will correctly compute whether one is subsumed by the other. Basically, it'll prove theorems involving combinations of these expressions. Okay, so now for those of you who read the abstract for this talk, you may have noticed that so far I haven't discussed at all anything in that abstract, which was all about, what does this have to do with data? I know that most of you are not interested in description logic and SNOMED classification and the SNOMED terminologies and
That's not true at all.
things like that, except for maybe one of you is interested in that. But that the thing I'm interested in coming to you with is this model and algorithm. How can this be used to process data, to query data, to classify data? How can this be applied to actual data to do other things that people who work with data and analyzing data and who are data scientists might be interested in? So the question I come to you is, can this temporal data model subsumption testing algorithm be used to execute temporal queries against patient databases, against actual data? So what? Oh, here's an answer now. Turns out, no. Sorry. Turn this off. So, for example, for clinical decision support, let's say you wanted to have a query in your decision support rule that says, does this patient's data match the pattern? This infection is occurring during the first or third trimester of the pregnancy. Because if it is, then I'm going to give certain advice, and if it's not, I'm going to recommend something different. So can we match that pattern, that temporal pattern between two events, to actual data sitting in our database for this patient? Or for research, this could also potentially be useful for research. We look in our database, find all the patients whose data matches the pattern, infection during first or third trimester of pregnancy. Use this model algorithm to do that. Or even for machine learning, here I'm out of my depth, so I'm just hypothesizing here. Let's say we wanted to classify the risk of infant death based on various factors, including the existence and timing of maternal prenatal infections. Can we pre-process data? Can we curate our data in our database? And for every patient, for every case of infant death, can we look back at the mother's patient record and determine whether, one feature in our model is whether that mother had infection during the first or third trimester of pregnancy. And if they did, then we put 1 in that feature. And if they didn't, we put a 0. And we just have that part of our model because there could be a signal there or not. Or there could be all kinds of other temporal relationships between events that we may want to derive, abstract out of the data as features in our machine learning model. So how would we do this? So let's say we wanted to ask the question of particular patient's data, this query term about first or third trimester infections. So we formulate the query. Here I kind of have it in logic terms, but you can imagine how this might be done in something resembling SQL. We would say, is it true that exists X, two instances, 2 rows, basically X and Y, such that X is a maternal infection, Y is a pregnancy, and the temporal intervals of these 2 events satisfy this particular relative temporal relationship that we talked about earlier, that I just got done describing. This is the way, again, that you would represent that an infection started in the first trimester, started in the third trimester of a pregnancy. How do we query a timestamp database using that notion and the machinery that we developed earlier, that we talked about earlier? So one way to do that, think about it is so here's our timestamp data. So a couple things to notice about this data. So here's just a table of infections, let's say, different patients, and the start date and end date time of infections they have, and it's at the granularity down to a minute. But some of the fields are null. It's like in data, sometimes you won't have the data. It's null, or either this infection might still be going on, so the end date is null. Similarly for pregnancies, you have the start date, which is typically the LMP, last menstrual period date, and the end date is when delivery took place or the pregnancy was terminated, if that's recorded. And again, you might have some null values. And also note here you have a different granularity of time. You just have the day, not the hour and minute time. So in fact, the method that I'm about to show you works for this, even if the temporal granularities are different between the events you're comparing, and some of the timestamps are not available, they're null. So how would you take this timestamp data? What you really need to do is, let's say we're looking at a particular infection and pregnancy, where we want to apply this algorithm, this model and algorithm, to determine if that particular pair of events satisfies this temporal relationship. So in order to do that, we basically have to derive generalized relative temporal relationship like this for that pair of events, given their timestamps in the database. So how do you do that? So you start by computing the intervals for all the beginning and ending time points, the 4 different intervals for these 2 events at their lowest level of granularity. So again, the start and end date times of the infection are down to the minute, but our lowest level of granularity is seconds. So we basically have to impute that the start time is actually a range between 0 and 59 seconds of this minute. 0 and 59 seconds of this minute. Similarly for this and then time, we impute this range at the level of seconds. Here we just have days, so we have to also impute a range from 0 hour on that date to 11:59:59 on that date, and same here. So now we have comparable timestamps, ranges of timestamps for the beginning and end points of these 2 events. And then we take those, because we know those timestamps, now we can compute the parameters for these predicates for those 2 particular events, for that infection and that pregnancy. And we do that by basically these ranges you can think of as at the beginning of event X, somewhere in this range. The beginning of event Y is somewhere in this range. So the difference between them basically is somewhere between the minimum difference, their closest point, the maximum difference at their furthest point. So we can just calculate this for the beginning, the interval between the beginning of event X, beginning of event Y is greater or equal to this minimum difference, which we can compute just by taking the difference of these two date timestamps. And it's less than this maximal difference, which we can again compute by taking the difference between these two timestamps we've imputed for these events. When we do that, we see, calculate this out to seconds, and then we can convert it to weeks because of those conversion factors readily enough. And then we can express it as relative temporal interval predicate. And we can do that for all four of these types of relevant temporal interval predicates for these two events. And then once we have that, we just apply the subsumption algorithm to determine is this relationship between the infection and pregnancy subsumed by this relationship, which is the pattern we're looking to match. And if it is, then that's a hit. If it's not, then it's not a hit to our query. Lastly, if we consider this case where there's null data, what's happening there? This model is resilient to the endpoint for the pregnancy not being there. Basically, it can still calculate those relative temporal interval predicates. How does it do that? Well, again, so here basically we don't know this. We don't know anything about the end timestamps. We know the other things. So we can still calculate beginning to the beginning and the end to the beginning, but we can't say anything about the beginning to the end and the end to the end. So essentially, we end up with just some statement about beginning and end to beginning. And remember, that's okay, because we can normalize it using our implications for those relative temporal interval predicates. We can derive the constraints for involving the end point of that pregnancy. It'll be very broad because we don't know anything about it, but we know a little bit about it because we know it can't be before the beginning of the pregnancy. But that tells us something about the ranges that are allowable for those relative temporal points.
Well, we've actually just got a couple minutes before the hour ends, or if you want to.
That's my last slide.
Okay.
I just want to talk about future work here real quickly. So what we plan to do is, we haven't even implemented this yet. So we plan to implement this model and algorithm, explore integration of it in description logics, like I talked about, such as OWL and ELK reasoners, explore integration of it in query engines, like I talked about at the end, and then possibly extend the model and algorithm with things like negation. Right now you can't say things like not during first trimester of pregnancy. Is it worth doing that, and how would you do that? And any other ideas folks may have. So that's it.
I was thinking back to the prior one, like, does AFib happen after lung lobectomy? And I thought it would have fit because I would have said after the start of the lung lobectomy. I can imagine there's all sorts of vagaries on what's being reflected. And is what you're going to do here, this sounds like I'm writing a lot of SQL queries that have to do this kind of stuff. Maybe you have a model that can generate the query parameters, basically.
That's exactly what you don't have to write the SQL query.
Yeah, and I'm always like drawing on a paper, right? Timeline is like this. So the start was before. I've done that exercise many times. I can imagine that kind of logic to represent.
I mean, you can imagine, what if there was like a module that did all this, and you could just say, here's the pattern I want to match.
Yeah.
Here's the data. Here's where the start point and end point is in the database. Now figure everything out.
Yeah.
And it was just pre-programmed to do that. And it could be. So that's the idea. That's what I'm curious about. If there could be value in taking an implementation and trying to do that with some of the data things that you all are doing here, some of the analysis.
Translate words to code basically is often, I mean, that's often our jobs to do that, but you can imagine it's gonna be a reasonable approach to doing so.
Exactly. And it's very error prone too, all the SQL queries and all the different temporal, comparison operators, and there are different granularities and some data is missing. What do you do with that? This can, you can encapsulate all that root logic in a module that applies this reasoning.
The first question, we are right at the hour.
Yeah, so are there any off-the-shelf classifiers that will actually allow you to reason over relations as opposed to?
Oh yeah, they like ELK does. Like SNOMED, the SNOMED classification algorithm does that. That's part of the SNOMED model.
Really? Okay.
It's part of
Cool.
EL or whatever. But no one does it because you can't really reason. There's no, can't define a temporal relationship. Can't define a relationship. You can only assert classifications of it. Whereas with concepts, you can actually define them in terms of other concepts. So that's the whole idea here. Can you create something analogous for temporal relationships, so you can define them and then compute their subsumption rather than just having to assert all those that hierarchy.
Very good. We'll continue the discussion ongoing afterwards. Let's thank Dr.
Yeah,
Sujansky.
absolutely. Yeah, thanks for your.
Why does the FEA want this?
Well, because they're interested in